To everyone out there watching and subscribing, thank you for doing so. I am Mr. Ish. We're looking here at type 2 improper integrals. You can say this will be a comprehensive introduction to type 2 improper integrals. We have the distinct advantage now, having looked at type 1, that we can get to the main concepts of this without too much preliminary formality. Type 2 improper integrals in a general sense will be those where the interval has a certain infinite discontinuity at play, which will normally arise as a result of a vertical asymptote. Just look very quickly at this function right here. It can just be f of x. We're looking over here at an interval a and b, but I'm not drawing the parentheses just yet because I want to show you something. A is right here and b is a value right over here, but unfortunately it kind of runs through a asymptote. In this instance, when you're looking at this, and we could arbitrarily draw a function which would look and go in that direction right over here. We could draw this in terms of this interval from a to b, right, as in this manner. You see how we have to include a circular parentheses around b because b would not be within the domain. This would very well have been a rational function where the zero of that function ended up being the value b. Consider this other one right over here, and again I'll do a comma b, but in this instance we're looking at a representation which very hypothetically is from here a to b, but here a ends up being a vertical asymptote, x equals a, x equals b over here, and your graph was going in this direction. Remember, these are just hypothetical examples. We're looking at an interval here from a to b, and you know we're looking at all of this shading, all of that, and then going up over here. In this instance we're looking at all of this shading and then it's going up. Here your interval will look something like this with regards to how you would set this up for your integration procedure. But notice how we have the parentheses coming into play based on from which side you are arising from and from where the asymptote is present. If you were to set this up here in terms of a integral, you could very well do so now applying the limit. Generally here you'd be still saying in terms of a integral f of x dx a to b, but this is meaningless here because we haven't employed the limit in here. We can modify this very well now with the limit application, limit as t approaches b, but we're not approaching b here from the right, we're approaching it here from the left, so you have to put this little designation. And now what do you end up having? A to t f of x dx. You see how everything has been modified? Coming over here and doing the same thing with the application of the limit. You could originally start out with something like this, a to b f of x dx, but this right here is meaningless because when you're looking at something like this and when you're looking at something like this, you're thinking of a definite integral involved with a proper limit. There's no sense that a improper limit is coming into play, or that you may have a situation as this, which is why you bring in the limit, right? You can do a limit as t approaches a, but you're approaching a here from the right, because you're looking towards the right of that asymptote, right? And then you're going here from t to b f of x dx, and you see how everything begins to take the form and the shape. We're seeing all of this play very well, similar to type 1 improper integrals, but here we have these distinct differences come into play, as you can see right over here, and as you can see over here, and as you can see due to the presence of this infinite discontinuity. It looks like an infinite discontinuity to me as a result of the vertical asymptote coming into play. Very likely these would have been rational functions, and the zeros are representing and generating these vertical asymptotes. You can say this is a function which is continuous from a to b, but it has this discontinuity at b. You can say here that this function is continuous from a to b, but it has this discontinuity arising at a. In both cases, of course, you can end up with a situation of convergence. You could end up with a situation of divergence. One would not truly know until they actually calculated this through to see what type of outcome we have. We have one more form to look at over here, and then we can look at one or two questions because I want this to be a comprehensive introduction. In a future video, we can actually take a look at good number of examples. Let's look at this representation where we're looking at an interval from a to b. For this function over here, which ends up having this vertical asymptote, we can just say this is a letter v. We'll represent that as v. We're looking at a case where a value in terms of numerical magnitude is less than v, which is less than b, like on a number line. This right here is ahead of a, and this is v is behind b, so we have everything here in this order. If you were to do some sort of determination here for the integral, and you know it's always related to area below the curves, you know you'd be looking at all of this area and then going up there, and then from there you'd be coming down and going in this. We have this infinite discontinuity here at play from A to B. How can you really express all of this with regards to this type 2 improper integral? Remember, type 2 improper integral will have some sort of an infinite discontinuity at play in your interval. You could look at everything like this. Let's use good notation over here. From A, including A, we're going up to V, but not including V. Then we're jumping over that infinite discontinuity. This is me just setting up how our intervals are with regards to notation, then not including V because it's outside the domain because you have an asymptote, then going up to B but including B. And with regards to now converting this into your integration setup, you would look at something like this. You go going from A to V, f of x dx. Remember, this is not my complete setup here. This is just me working towards that setup. Then from V to B, you have f of x dx. But again, this is meaningless or ambiguous in the sense it doesn't tell us right here. Just looking at this statement alone and nothing above it, we don't know if this is a proper or improper integral. But since we now know it is an improper integral, we can bring in a limit. And this is just a general way of doing it. It's a good way of doing it. Limit as t is approaching v, but t will be approaching v here from the left. Then you'll have a and then t here, and then f of x dx, and then limit over here as now t is approaching this v, but it's approaching it from the right, right? T is approaching v, but from the right you have t coming here, and then a b, and then f of x dx. What does this limit t approaching v and all of that really indicate over here? It basically means you're just finding some value very close to this v, and then you're working your integration procedure area under the curve up to there, and likewise from this side you're finding some value over here close to your asymptote but not on your asymptote, and you're doing your integration procedure up to there. Then you're slowly applying the limits to see as you got closer and closer to your asymptote, which here is the v, what would happen to everything with regards to convergence and divergence. That right there in a nutshell is what this limit is really doing. But we have this setup over here now created. What we need to do now is put some of these setups to work by, I think we should just do 2 questions in this video and we'll see how everything plays along. We'll start here with this good question. It's a good exemplary question because it'll put some of what we've talked about to work. Remember again with regards to type 2 improper integrals and type 1 that concept of convergence and divergence stays the same. If a limit exists, you will end up experiencing that convergence come into play. If the limit does not exist for that function you're looking at, we will end up seeing divergence, and then we won't be able to actually calculate a good finite value for that area we're talking about. Here we have an integral from lower limit 2 up to 5, 1 over root of s minus 2 ds. We shouldn't always be used to looking at x in terms of our variable. It could literally be any letter. From now on, anytime you're seeing a question like this and a definite integral, you should always be thinking in your mind, is some sort of a infinite discontinuity at play, or are you dealing with improper or proper integrals? All of that should be working through your mind as you solve something like this. When I'm looking here at the denominator, I'm looking, if I were to zero this out, I know in terms of the domain, s cannot be 2 because I would zero out the denominator and I end up seeing a vertical asymptote at a value of s equals 2. Here's my s equals 2 is a vertical asymptote. Now I don't really know how this graph will truly draw out, but I can surmise it would very well be in this direction right over here, going from 2 up to 5, and let this be 5, and here is 2. We're looking at this interval here. How can you show this in terms of just notation? You're looking at like this, 2 up to 5 including 5, but 2 is not included. We're looking at all of this right here with regards to area below the curve. That's what we're looking at. So always do zero determination to see if a vertical asymptote is at play, and if it's somehow part of your total interval, then you know you have a type 2 improper integral at play. Alright, let's get to it. We know we have this coming into play in terms of an asymptote, so your curve will never really reach it. It'll try to get close to it, but it'll never make it up to that. We know here we're looking at this type of representation. Limit, as we'll use the letter t, is approaching this 2, but we're approaching this 2 here from the right. We have something which looks like this, 5 and now t. This has been replaced by t. We have 1 over s minus 2 root ds. What is the antiderivative of that? Well, let's just do that here on the side. 1 over root s minus 2 is no different than you doing s minus 2 here to the power of minus 1 over 2 ds. Do n plus 1 divided by n plus 1 because everything here with regards to derivatives is easy. You'll have n plus 1 or n plus 1, you'll have s minus 2 to the power of 1 over 2 divided by 1 over 2, you'll have 2 root s minus 2. This right here would be your antiderivative of that. We have our antiderivative already. Limit as t approaches 2 from the right, we have 2 root s minus 2. We're looking here at everything from 5 and t. All we have to do is the application of these definite intervals and see how everything plays out. Technically you could push the 2 outside, but we don't have to. We're looking at 2 and then 5 minus 2, right? Minus, then we're looking at 2, the lower value now coming in. We have 2 minus 2. Think about it. 5 went to place of s. T, which is 2, went into place of s. You're doing the difference of the 2, which is right here. This is a 5 minus 2, which is a 3. 2 times root 3. Well, I'm getting that. Here I'm getting a 2 minus 2 square root of 0. You can do that. 0 times 2 is a 0. So we end up getting over here as 2 root 3 for the value of this representation here, which you know will now represent very well a convergence, because you can actually state with some confidence or good confidence that limit existed for this representation, and you can do a good finite representation of the area for this representation, and that's 2 root 3. So this is a type 2 improper integral which succeeded in the sense that we have convergence and we have a finite answer here to present. We have an infinite discontinuity here at play in our interval, and we can present our interval in this format right over here. This is another good exemplary question to present because it will actually strengthen the concepts presented in this video. We have this 0 to 3 integral ds divided by s minus 1. If you do from now on as you will the 0 determination, s minus 1 equals 0, s equals 1, we know now that we have a vertical asymptote at play. And look how the interval is with regards to this asymptote. Vertical asymptote is s equals 1. We're looking here from 0 up to 3. That's our interval, but our interval has within it, somewhere in the middle, but not exactly in the middle, an asymptote. I don't know how the graph would be over here, but we can assume that in some way the curve is coming towards the asymptote from one side and it's coming to and continuing to the other side. Imagine this were the graph, but I'm not sure in my head exactly how it is, and from 0 to 3 with this 1 in between. What we can do is now create a setup of what everything will look like. And look, we're looking at something which looks like 0 up to 1, not including 1, and then 1, jumping across this discontinuity from 1, not including 1, going up to 3. And let this be the guide as to how you will present your setup. You'll go from 0 to 1. This is just a very rough representation here only. And then from 1 to 3, f of x dx. But again, this right here is ambiguous. Imagine if you didn't even do the 0 determination and you treated this as a proper integral. You'll take this and you'll actually get a good value. And let me do this as a incorrect manner first. We're looking at the antiderivative of 1 over s minus 1 would be natural log of s minus 1. This is us thinking that there's no discontinuity, there's no vertical asymptote in play, and we're doing all of this. And you end up getting over here natural log 3 coming in and 0 and the difference. You'll have natural log of 2 minus natural log of 1. And you would here present that your answer is natural log 2 as the area, and this right here would be wrong because you're treating this as a proper integral and you're not thinking that there's a 0 and there's a vertical asymptote at play right in the relative middle of your interval that you're looking at. So this right here is wrong. You can't go in this way anymore. Let's bring in our limit. Limit as t approaches this 1 from the left. We're looking at 0 up to this t. And then we have ds over s minus 1. This right here is an easy antiderivative, and you know it's going to bring the natural log. Limit as t is approaching this vertical asymptote but from the right, or approaching it from the right and approaching it from the left in these two separate parts. Here you'll have t up to 3, right? ds over s minus 1. Let's bring in the antiderivative in the next step. The antiderivative we know is natural log. Bring in the absolute value parentheses so you avoid the situation of bringing a negative in place of a value that should be hit by natural log. So use the absolute value. We have s minus 1, and you know we have this limit as t approaches 1 from the left, and we have these upper and lower intervals t and 0. You got this plus sign. Then limit as t is approaching the value of 1, the asymptotic value of 1 from the right. We have again the natural log and the absolute value s minus 1. and you can bring the intervals t and 3. With regards to these natural logs, you'll have a little bit of work which will come into play with the upper and the lower limits and the difference of the two. We'll look at this part right here first. When you do t minus 1 over here, you're looking at a 1 minus 1. You can have a natural log t minus 1, which is a 1 minus 1 is a 0. Minus, then you're going to put a 0 over here. Natural log of 0 minus 1 is a natural log of a minus 1, but the absolute value will make it a positive one. We have this plus over here, and let's bring in the 3 and the t and the difference of the two. Natural log 3 minus 1 will be a natural log of 2 over here. And then we have this natural log t coming here, t minus 1, which is a 1 minus 1, natural log of 0. When you're basically looking at all of this, you already know if we have a divergence at play. Because I know natural log 2 is a good number, but this right here is a undefined number. You cannot do a natural log of a 0 is undefined. Natural log of this 0 is undefined. You can certainly do a natural log of 1, which is a 0. You're basically seeing an undefined, which we can represent here as an infinity minus a 0 plus natural log of 2 minus infinity. All of this right here certainly brings you to a very good conclusion that we have divergence over here, that this expression here, that this entire integral, definite integral, cannot be evaluated in terms of the area below the curve, because a limit is not existing over here, because we have divergence here. When you came right here to this very first step and you started doing this, the minute you saw this natural log of 0 bringing in this infinity, you could very well have ignored the rest and not even bothered wasting a minute or two doing the rest. This right here alone would very likely have given you the divergence for the entire process that would have followed. Here your answer truly is divergence. This definite integral is divergent. You cannot have a good determination here for the area below the curve that's involved. For 0 to 3, you have a vertical asymptote in between, and a limit will not exist for this case over here. So keep in mind everything we've addressed over here with regards to type 2 improper integrals. They're not certainly that hard. Once you know type 1 improper integrals, type 2 are relatively easy. The only difference being here is that you're thinking about an infinite discontinuity at play within your interval, and that infinite discontinuity is going to affect your entire procedure such that you're looking at interval notation such as this, and you're looking at limits such as this, where you might be approaching something, the asymptote, either from the right or from the left, because at that specific asymptote you may not likely have a right and a left hand limit existing, let alone that they would be equal. You would only have a one-sided limit, and generally for the divergence cases you'll have a limit that will not exist at all. But type 2 improper integrals can give you values of divergence as an answer, and you can see convergence as an answer. I appreciate everyone watching this video. Thank you. Have a nice day. Bye.